last keynote session of the conference, of this IMAV 2021 conference. And I have the privilege of introducing to the audience to one of the most recognized researchers in Mexico, who specializes on the field of unmanned aerial vehicles. So we have with us Rogelio Lozano. And Rogelio Lozano got his BSc degree in electronic engineering from the National Polytechnic Institute of Mexico in 1975. The Master in Science degree in electrical engineering from the Centro de Investigación y de Estudios Avanzados Investa, Mexico in 1977. And the PhD degree in automatic control from the Laboratoire d'Automatique de Grenoble, France in 1981. He joined the Department of Electrical Engineering at Investa, Mexico in 1981, where he worked until 1989. He was head of the section of automatic control from June 1985 to August 1987. He has held visiting positions at the University of Newcastle, Australia, from November 1983 to November 1984. Visiting position at NASA Langley Research Center from 1987 to 88, and Laboratoire d'Automatique de Grenoble, France from February 1989 to July of 1990. Since 1990, he is CNRS Research Director at the University of Technology of Compiègne, France, and he was Associate Editor of Automatica in the period of 1987 to 2000. He is Associate Editor of the Journal of Intelligent and Robotic Systems since 2012, and Associate Editor in the International Journal of Adaptive Control and Signal Processing since 1988. He has coordinated or participated in numerous French projects dealing with UAVs. He has organized 2 international workshops on UAVs, IFAC Red US 2013 and Red US 2015. He participates in the organization of the annual international conference, ACUS, the International Conference on Unmanned Aerial Systems, since 2010. Since 2008, he is the head of the joint Mexican-French UMI 3175 CNRS, and his areas of expertise include UAVs, mini submarines, exoskeletons, and automatic control. He has been the advisor or co-advisor of more than 35 PhD theses and published more than 130 international journal papers and 10 books. And on the top of all of that, I have to say that Rogelio has always supported the community. I remember in 2017, we organized a workshop on control and vision for autonomous drones here at INAUE. And we asked him to open the conference, and he accepted and came to deliver a very nice keynote. So it is nice to have him again. It is unfortunate that we didn't manage to run the conference physically, so because of the pandemic, but at least with the magic of internet, we have him with us. So without any further delay, Rogelio, thank you very much for accepting to deliver this talk, and please go ahead. The stage is yours.
Okay, well, thank you very much, Jose, for the invitation. It's a pleasure to be with you. So let me, I'll put the slides right away of this, of the talk. Let's see. Let's see. Okay.
Great, we can see them.
Okay, so we are in the first slide. Okay, well, this what I wanted to was to present the subject of this subject was the subject of a PhD thesis that was presented this year in Mexico. In this, as Jose was saying, this is the LAFMIA. Well, used to be the what is called today LAFMIA in Sindestat, the Center Center for Research and Advanced Studies of the National Polytechnic Institute in Mexico City. So Jonathan was is the main he got the PhD this year, and this is a joint work also with Sergio Salazar. So the topic is as follows. As you know, you certainly know the quad rotors that have in the past, I don't know, 15, 20 years appeared and are now very popular. And at least, I mean, in the small size, they are even more popular than the classical helicopters for small prototypes. And one of the reasons for this, and let me put the next slide. Okay, as I was saying, the quadcopters gain popularity. In my point of view, one of the reasons is that that quad rotors are mechanically simpler than helicopters. So those of you that have tried small classical helicopters know that they are. When you drop the helicopter, when it crashes, it takes a lot of time to rebuild the helicopter, because there are many mechanical pieces that get damaged. So I remember when we playing with a small helicopter, and then when you start learning, you crash, and then there's many pieces that like for instance the main axe, it bends. Of course the blades broke, but that's not the most difficult problem. But then what is called the swash plate, it also breaks, and so you want to repair a small helicopter after a crash. It will take a few days. And then on the other hand, quadcopters, they are simply, well, you basically have the frame that never breaks. I mean, it's hard to break. And then you have 4 motors. And basically, when it crashes, basically you have to change the blades. The motors, they don't break. I mean, they don't break, and then it will take a few minutes to repair a quadrotor. Of course, helicopters have some advantages. I mean, since they have a large rotor that covers a large area, then they produce more thrust. Okay, and then that explains why they have longer flying times. So a helicopter can fly longer than a quadrotor. That's my understanding. Of course, quadrotors. I mean, when you to control a quadrotor, you basically have to deal with changing the speed, the angular velocity of the rotors, and for that, unfortunately, you require. You require the rotors to be not so big, because if they are big, it will take long time to change the angular velocity of the rotor. So it will be a rotor. I mean, if you try to build a quadrotor, with large blades, then it's going to be as the blades get larger and larger, you will run into problems because you will not be able to control it easily. So there's a trade-off in the size of the blades. So the idea in this paper was to go back. I mean, the main idea was to go back to the classical helicopter structure, that is a large rotor, and then a small the small tail rotor to control the yaw, basically. But try to solve the problem of the. I mean, to try to have something that is mechanically simpler than a classical helicopter, so as to try to, well, to see if we can get a different configuration that is perhaps in the middle, in between a quadrotor and a helicopter. Okay, that is the purpose of this work. So so how does it work? I mean, you have a photo here on your right. You have the motor, and then these white pieces made of plastic. Well, yeah, plastic, and then it has. I mean, as you can see, there are some. They are called hinges. I mean, this piece here is called hinge, and it's skewed. I mean, so we'll see another figure that, so that you understand what is going on. So these black pieces are the blades, but the blades can turn depending on the angular velocity and the well, I'll explain this in a moment. So and that's all. I mean, this is the mechanism. As you can see, is rather simple as compared to a conventional swatch plate. I'll describe later what is a swatch plate. This control technique started some years ago, but for some reason, I mean, there has not been a lot of development. So that's why we started to work on this area. Let's see. So okay, you have here. This is a rotor that is being controlled. So well, the first, let me start again. Okay, so this is, I'll start again. Let's see. Okay, so let's start with it. This one is rotating at a constant angular velocity. And this is, as you can see in this figure. And in the figure below, the rotor is turning, changing the speed. As you can see that it slows down a little bit, and then okay. So this we will use this phenomena. We will modulate the angular velocity, and then. Here is again the skewed hinges. This mechanism is such that that when you accelerate the rotor, the blade goes forward or backward, and then the inclination of the blade changes. So this is what replaces the standard. Okay, here we have in your left we have a classical swatch plate. So here are the blades in this. I'm sorry, let me go back. Okay, here are the blades, and this part here, all this part is called a swatch plate. So with these black pieces here, the blade pitch is changes, okay? And here, this mechanical piece goes, is moved by a servo mechanism. So basically, you have 3 servos, one moving this piece, one moving this other piece, and there is another one that moves the whole, this part here up and down, okay? So, okay, that's what it's called. This is just a classical swash plate. And this is what we're using in the helicopter that we are building. So as you can see, this is just a very, these pieces have been made in the lab with just, it is made in aluminum, and it doesn't break. It's very strong. And these are the blades, okay? So we're trying in a way to get back, this property of the quadrotors that are robust with respect to when in a crash, it doesn't get damaged. Let's see. So here is an explanation on how, when the angular velocity, when you change the angular velocity, these the blades go back, move backwards or move forward, and that because of the way this pivot is working, the pitch of the blade changes, okay? And then on one side, for instance, let's see, well, on one side, when you accelerate the rotor, the blade pitch increases, and on the other side, the pitch blade decreases, and this produces like a pitch momentum. Okay. So this is just a flow chart for the virtual cyclic swash plate that we have made. So here you have so the helicopter will have the standard tail rotor, which is here. So this is to control the yaw displacement. And then the main rotor will be as here with this virtual swash plate. And then it requires some additional thing as we require to measure the rotor position. Okay, so we include a magnetic encoder. Okay, this is in a standard quadrotors or classical helicopters. You don't require this device to measure the position of the rotor, but in view of the way this swash plate works, we require to know the exact position of the rotor. And then, of course, there's the microcontroller, and then yeah, the rest of the equipment is more standard. This is just to tell you the range of the frequencies in which these things are working. So the autopilot is working at the range of 50 Hertz. Here's again the device that measures the position of the rotor that works on Hall effect. And of course, we're using pulse width modulation to change the to replace the to produce the pitch control of the rotor. So here's again the helicopter diagram, the forces, etc. You have here the force generated by the tail rotor, and then the rest. It looks like a standard helicopter. It's just that the swash plate has been replaced. And of course, as I was saying, the tail rotor is controlling the yaw of the helicopter, as in a classical helicopter. But here, the virtual swash plate is controlling the pitch angle and the roll angle of the helicopter. So, well, this is the way that the signals, as in a classical helicopter, you have, of course, you have then three signals basically. One is the average thrust of the blades, and then you introduce these sinusoidal signals on the blades. So let's see, just to produce the whole blades disc to move forward like here, or you can also move with this virtual swash plate. You can move both. You can produce a pitch momentum as well as a roll momentum. Okay. And here are some experiments. So here is this is the first experiment of this classical helicopter. This is in Simvestav area. Some of you may recognize the Chiquihuite hill. And this is a second flight of this. So perhaps it doesn't fly as well as a classical helicopter, but this helicopter is very robust, and then Jonathan has flied this and has crashed several times, and he repairs the helicopter quite, very fast as compared to a classical helicopter. More recently, students have been working in a different configuration. I will try to show it to you. Let's see. Okay, here are some. This is instead of having the classical configuration of a helicopter. Let's see. I'm not sure you can see this. Let's see. Okay. Sorry for the. Let's see.
This work introduces
no, this is not what I wanted to show you. Okay, well, here is another video of this is a helicopter in tandem that has the two rotors have this virtual swash plate, and here is as you can see, they are controlling the pitch. This is a very recent work. but I mean, they have not yet been able to fly this tandem helicopter. And this is just for the pitch control. And there is another, let me see if I can show you. This was not working. Let's see what. Okay, here it is. This is just to show you. This is again the tandem helicopter. There are two rotors, and you'll see some movement of the blades of the rotors. So here both rotors are moving to the left and to the right, and they also can move in opposite direction, like here. This is to control the yaw. So as you can see, by modulating the angular velocity, you can change you can produce some moment either to move the pitch or to move the roll or the yaw. Sorry. Okay, let me go back to this. So it's, basically, this is what I wanted to show you. So, Jose, if I think we can, I mean, if anybody has a question, I'll be happy to try to answer.
Thank you, Rogelio. If anybody from the audience here in the virtual room, if you have a question, please, you can send it to me in the chat. To me, the very first question I have, and might be a very silly one, is just because you showed this last vehicle with the two rotors. So what about a quadcopter? Would that be possible? This is not necessary. I mean.
Okay, yes, sure. Yeah, well, I suppose it's possible. I think that, well, we also had in mind the following thing. I mean, very often these quadrotors are used to I mean, you are used to carry a camera. You want to get images of a place. And then one thing that some of you that have been work with these quadrotors have noticed that the camera moves a little bit. So so sometimes, I mean, the noise produced by rotors increases as the number of rotors in the prototype. I mean, if you have 6 rotors, you will have some more frequencies, more noise. So in a way, so there's always a trade-off, I suppose. I mean, in some sense, we were interested in reducing the number of rotors and dealing with a main rotor that has large blades. So it's I suppose it depends on the applications, but of course you can also try to use these ideas. Yeah, you could perhaps use these ideas with more rotors, like 4 rotors, and each one of them you can use a virtual swash plate to increase the number of possibilities. I mean, you have plenty of control inputs to move that's another type of application where you could a standard quadrotor has just you can, as I was saying in the beginning, you want to I mean, you basically change the angular velocity of the rotors to produce a pitch moment or roll moment. But if you use this this virtual swash plate, perhaps you could, I mean, you can have large rotors. Yeah, I think it's not so silly. Your question is not so silly. Maybe there are some possibilities to have some properties of a prototype.
Well, I was then thinking of a second option, which is what about this type of hybrid vehicles, you know, like the ones that take off vertically and then they transition into fixed wing.
Yes, yes, that's another interesting possibility. I remember, well, I had another student working on an airplane that was supposed to be a hybrid in the sense that it will take off vertically, and then after transition it will fly as an airplane. And one of the things we were, I mean, you may have different configurations, and the configurations we wanted to have was to have an airplane with will have the main wing will rotate.
Mhm.
It will move. I mean, you in order to take off vertically, you will have the wing with the rotors on the top, two main rotors, and then you will take. I mean, the prototype will take off like that. But one of the problems was that with two rotors, we don't have enough pitch moment, and then we had to add. Well, not so. I mean, one possibility was to add a third rotor in the tail, and the other possibility was to use the ailerons on the wing to produce pitch moment. So it was and as you was just suggesting, we could perhaps use I mean these virtual swash plates. We could have two main rotors in the wing that are with these virtual swash plates, and then this will generate some extra moments, and it will be useful in the takeoff part, because then you have additional moments. Yeah, that's another idea that in the future somebody has to explore. I don't know if I would have a student on that, but that's a possibility.
Okay, thank you, Rogelio. So please, for the members of the audience, send your questions, and in the meantime, I keep asking. I have the opportunity to ask you these things while we wait for somebody in the audience to ask something. But what about the scalability of this approach? Because you are showing this in this micro helicopter, but can it go in larger sizes?
That's so far. I mean, well, as you can see, I mean, if you look in what is, there are very few prototypes like this in the community. There's very few. I mean, maybe there is a reason for that. I mean, the development it always takes time, and perhaps there are. I mean, perhaps there's these first prototypes are a bit noisy. There are vibrations. They might have some. Also, something that I have to say, to point out, is that there's still we still need to study the energy that is used to produce this. I mean, when you use this virtual swash plate, you move the rotor, you modulate the angular velocity, and this takes, of course, energy from the battery. So it has to be. I mean, it's something that has to be taken into account. So it's this. You get some advantages, but they are not free. So you pay for this in terms of energy. Perhaps this prototype needs more energy. I mean, it's perhaps more robust than a classical helicopter, but the price to be paid is that you have to, this modulation requires energy from the battery. Okay, and now the scalability, I really don't know. There's not that as far as I know, there are no large helicopters of this type. But on the other hand, it's interesting that this helicopter is mechanically very robust as compared to the standard helicopter.
Yeah, yes, sorry, go ahead.
Yeah, that's something that is interesting, because then, well, at least for these small sizes, you can crash your helicopter and then repair it in one day or in a few minutes. You will only have to change the blades. So that's a big difference with respect to a classical mini helicopter.
Yeah, certainly. That's why I thought your presentation was very suitable to the conference, because this conference specializes on micro air vehicles. That's the main topic. It has been the main topic for 12 years now. And in fact, you should know the Black Hornet Nano vehicle, this very small helicopter as well, right?
Yes.
So I was thinking that maybe that was your niche, like to develop something like that vehicle. What are your thoughts on that?
Well, I never understood how that little helicopter worked, really. I just knew that it was very expensive.
Yeah.
And that not anybody could buy it. I mean, certainly not a university could not buy it. It's only military uses.
Yeah.
Very expensive. And I don't know. I don't remember. I looked at them. I don't remember. I don't think they have a standard swash plate, but I don't know if they have this type of virtual swash plates. It's a good question, because we thought about it a lot, and maybe they have some sort of virtual swash plate. But there is a lot of not a lot of things are known, because it's a military application. And so as you can see, in your questions, there's the question of building larger prototypes with this technique, or smaller prototypes. In both sizes, there's something interesting to be found.
Yes, especially because of this thing of the energy. I guess if you go to the micro world, or even the nano world, and perhaps you get certain advantages. And I was thinking of that vehicle in particular, because the developers of that vehicle, they were part of the IMAV community for some years. As far as I remember the stories, they started out in this conference. They came to this conference many years ago to show their prototype. And then we saw them in France in 2017, when the IMAV was organized in Toulouse, France. The CEO of the company, he came over, and actually he showed the vehicle. It was, I had never seen it in real life, and he showed it. But as you are saying, like, it was just showcasing the vehicle, no secrets unveiled. But yeah, this one reminded me a lot of that type of vehicle.
Yeah, maybe there's something. I never understood how it worked. It was very small, and you could not see a standard swash plate. So it was not clear.
So sorry.
It was a lot of secrecy about it, I think.
Yeah, the only thing that we knew is that it was costly, was very expensive.
Very expensive, yes.
Yes. So you mentioned this issue with the cameras when you were explaining the vibrations. if you have one rotor or multiple rotors. And in this case, are you planning to test how a camera would behave with a drone like this?
With this prototype, I mean, there's another student is, as you see in one of the videos, there are two students. One is Jonathan, who got his PhD, and the other one is a new student in a master program. And so what we were planning was, I mean, we think that as you could see, they are working on a tandem configuration, and this configuration is supposed to be even more have longer flying times, and we wanted to get something that will fly for longer times, and that's a master thesis of this student that just started. And but we're more working on. So there's another video where they are trying to make it fly, and so far is not working so well, and so it needs some more time, some more development. But what I want to say is that at this moment we don't have a prototype that is working properly, so that we can put some cameras. We're not yet there.
Yeah, I was thinking of that because, well, the first application, the first obvious application for external users is just to put a camera on board, right, to get some footage. Sure. But then I was also thinking, since you were talking about helicopters, whether how would it work in terms of the control theory that we have used if the vehicle had to lift something, you know, like cable suspended loads or or a robotic arm, I don't know.
I mean, my first answer would be that it has, as quadrotors and helicopters, this new prototype has again the same controllers, the same control inputs. I mean, the total thrust. You have one total thrust, and you have three couples, like the pitch, roll, and yaw couple. So basically, it would seem that you could use the same type of control algorithms. But of course, if you go more in detail, then there are new issues that may appear because the control is performed differently because of this angular velocity modulation. But that's going more deeply, more inside the prototype. But from outside, it looks basically the same.
I see. Well, that's a big advantage.
Mm-hmm. Yeah. So the main advantage, I would say, is that it's very mechanically robust. And then that's for at least for quadrotors, in my point of view, that was one of the main things that made that we have quadrotors everywhere now.
Yeah.
And with classical helicopters, you don't get the same thing because it takes a lot of time to repair.
Yeah, you're right. I remember when I began working with drones, and some friends actually told me about them. They were very excited because they got one of these small helicopters. And then they were showing off basically their flying skills, because controlling one of these helicopters is very complicated.
Yes,
so I think it's quite similar to what happened with computers. You know, like at the beginning, computers were like only for people who specialize on how to use a computer, and then eventually it was for everybody. And I think the quadcopters they became like that. They are like the mobiles of of aerial vehicles, because then everybody could fly a quadcopter.
Sure.
Right. So it was not easy, and still I cannot fly a helicopter. I haven't learned the skills, whereas I can fly very easily quadcopters.
That is true. There's many people that can fly quadrotors, and they cannot fly a standard helicopter. It's different.
So that made me think of if you had to organize a competition around this topic, because in the IMAV, we have the conference, but really one of the most important aspects of this event are the competitions, the indoors, outdoors competitions. It's unfortunate that we didn't manage to organize it this year here in Mexico. We got everything, like we got the arenas and we got the, the large place for the outdoors competition. But well, unfortunately, because of the pandemic, we didn't manage to. But if you had to design a challenge around this topic, what would it be? Or what would you like to see?
Well, one of the main things is about flying time. I mean, how to get a device, a prototype that flies longer.
Endurance.
With endurance, yes, that's the main. And of course, well, in our case, is mechanical simplicity, but that's it's hard to. It's something that is important, but it's hard to put in a contest. But yeah, endurance will be one thing.
And for course, this, yeah, go ahead, please.
Yeah, and of course, simplicity in a way should be also. I mean, it's good to have a simple prototypes that can be repaired quickly and are not very costly.
Yeah, I think that is something interesting to look at, because as you mentioned, if you crash something, it would be very catastrophic, but then what matters is how quickly you can refurbish the whole thing and make it fly again. Because we may want to think of real scenarios where maybe, I mean, the most popular one is search and rescue, right? Something happened, an earthquake or something like that, and then you fly drones around the disaster area. And if the drones, because of the conditions of the environment, they crash or something happens to them, they get damaged. If you manage to recover them, you could fix them quickly and reuse them, because otherwise they become expensive toys, right? You try to use them for something real, and if you lose them, then people won't want to use them because they will be afraid of losing them and just money lost.
So that is true. I mean, that is the secret of the quadrotors. I mean, many students started working on aeronautics very quickly, and it wouldn't be possible with a classical helicopter. Of course, a classical helicopter is also a little bit more dangerous because it has this main rotor that is larger, and you have to be careful. And it's well, I remember some years ago, when I started working on UAVs, I bought a large helicopter, a Vario helicopter with a combustion engine, and it was, I mean, the student is now working somewhere in the north of Mexico, in Laguna, and his name is Zul, Alejandro Zul. And I remember that in order to get ready to make a flight, and when I say flight, it was really not on a platform that will only allow the helicopter to move up and down and then turn around. So it was a very limited flight. But even in that case, in order to get the helicopter ready to fly, I will need half an hour checking all the connections, all the screws and all that. I had to check that everything was tight enough. So it is during the day, I remember planning and putting my mind and saying, I have to do this. So it takes a lot of time in a classical helicopter, because you have to check the vibrations tend to, so the screws, I mean, you have to tighten again because of the vibration. So it is if you don't want to have an accident, you have to be very careful, and you have to be a hobbyist. I mean, have a lot of experience with a helicopter. You cannot just go buy one and fly it. You'll have an accident. See, so even I remember we took even to put this helicopter together. It was like what? I don't know. We used to work at the weekends, and it took us like 4 or 5 weekends. So it takes a lot of time, and you have to check all this. I remember I even had one of the screw that I had to check in the tail. You don't see it. I mean, it was very very hard to see. You will get access to the screw only when the position of the rotor was some specific one. So I forgot to check it. And then one day in this platform we had the tail that broke because this screw was loosened, and then introducing the mechanism, and then the rotor stopped, and then the whole tail twisted. So it has a lot of mechanisms. So when you see a simple quad rotor, it's a huge difference.
Yeah, definitely. I remember when I was doing my postdoc in the UK, we worked with a company called Blue Bear, and we did some experiments outdoors with an hexacopter. And before flying, they had to connect to the GPS, I guess, for the stability of the control of the autopilot. And we had to wait for some minutes, but really like maybe more than 10 or 15 minutes sometimes. And they would tell me, oh, it is because it's connecting to the satellites. It uses this very nice but old technology with satellites, but then it gives us very good positioning. And it was okay. So as you said, I mean, it's not as extreme as what you are saying, but to me, every time we had to go outside to do some tests, we had to wait.
Sure.
And now it is very easy. You just take off and that's it.
Yeah, it has changed.
It has changed quite a lot. So with that in mind, I would like to ask you a final question before we say goodbye, because I think you have a lot of experience in this field and you have seen the field, how it has changed over time. So what do you think is going to be the future of this field in terms of UAVs, but especially in this case, in the case of micro air vehicles? If you could share with us your thoughts on this.
Yeah, no, it's a very hard question. I mean, I have several students working on different fields, and what can I say? I mean, I know that companies are trying to get again the main. I mean, I have my son works in this area too, and the companies ask him to get prototypes that fly longer times. That's and that are how do you say? I mean, easy to use. I mean, for instance, very often, I mean, companies try to sell not just quad rotors, not necessarily quad rotors, but airplanes or wings. Wings are really inexpensive. So, and one of the well, the thing is, I'm very inexpensive. I mean, you buy a wing, and they are also robust, and you can fly them. I mean, you need a little bit more skills a wing than with a quad rotor. But one of the things that in order to improve the sails of the wings, you need that they are easy to be used, and then very often once they are in the air, it's more easy to control them. But taking off or launch, I mean, or how do you say it? I mean,
Landing.
Landing is a big problem.
It's tricky. It's tricky, yeah.
It's tricky. Launching is not so hard. I mean, you can. It's not so hard, but landing it takes some more skills from the people that buy this, and some people work on. They're trying to develop techniques so that you can land these wings or in general airplanes in a very short area. That's a challenging question. How do you do that? And it's like I mean, of course, some of us have been working on hybrid airplanes that can take off vertically, that can land also vertically, but they are more costly. So yeah. When you talk to an enterprise, what they don't want to see many rotors. They don't want to see many servos around. So it has to be extremely simple, and still they would like this. I mean, they wouldn't sell. For instance, well, I mean, I've been telling this around, but some people will not like it. But I mean, in our laboratories, very often, I have done this also with my students. We introduced rotors in the wing, many rotors, so that you can take off vertically and then move as an airplane after a transient. But in the world of the industry, this is not, apparently they are not interested, because it takes, I mean, it has to be simple. So there's a trade-off, and so that's a challenging thing, because well, quad rotors, I think, I mean, I don't see how they will change, but the airplanes, I mean, airplanes are also very useful because they can cover a larger area, larger than for a quad rotor. But then the problem is landing. You require a large space. So getting something in the middle, I mean, making airplanes or wings that can land in a short area is a challenging problem that I think some people will address this in the future.
Definitely, and one of the things that I thought about this subject is that I mean, with the issues of landing, taking off, endurance, you know, like the time you spend to get from one place to another, and you might run out of battery, and then when you arrive at the place that you are interested at, you have no battery. Sure. But then what about motherships, right? If you take a larger drone that carriers, all these type of small drones like the one that you have presented today, because then you save energy trying to reach the point that we are interested at, because then you just deploy them, they do their tasks. But you are right, if they break or if something happens, then the idea is that if they are cheap, you can recover them. Not only that, you can fix them and reuse them. So it would be a matter of how do you do the recovery, right? Because deploy them would be easy, I think, but to recover them, that's the issue.
Yes.
Great. Well, Rogelio, it was a pleasure to talk to you. I think the audience will find quite interesting this work that you have presented. I personally like it a lot. I didn't think of it, to be honest. I didn't know this type of work. Coming from the robotics field, perhaps we don't worry too much about these issues, these design issues. And here at the IMAV, we have people that specialize on that, and they have insisted quite a lot that not everything is autonomous flight with intelligent behavior. Design is also a very important side of the field. And I think you have proved them right. So thank you very much again for this opportunity and for your support. We will send you a virtual certificate for your participation. And I hope we can see you very soon.
Very well. Thank you for the invitation.
Thank you.
My pleasure.
Bye.
Bye-bye.
Take care. Great. So after this very nice keynote presentation, I would ask the session chair to take over, as we're going to have the last session of the conference, which is going to be Autonomous Navigation 2. So Fermi, are you around? Okay,
hello,
great.
Hello,
so
Jose.
Again, 1 minute late, sorry about that, but it was very interesting.
No problem.
Go ahead, the
It's very
station.
interesting, the talk delivered by Rogelio.
Very interesting indeed.
Okay, so thank you very much and welcome to this last session of IMAV 2021. So for this session, we have 3 papers. The first one is the paper number 5, Indoor Visual Semantic SLAM Improve Bio and RGBD for Narrow Space Navigation. So I wonder if the author of this paper is here. I don't know. Paper number 5, Indoor Visual Semantic SLAM.
We changed paper 5 and paper 6, so the
Yes, they change, Fermi. So yes, paper
Okay.
6 now. Please go ahead.
Okay, no problem. So thank you to be here. So, okay, you have 50 minutes, Miguel. Yes.
Yes.
Okay.
So I will.
Please, you have the floor.
Okay, so I'm Miguel Fernández Cortidas. I'm from the Computer Vision and Aerial Robotic Group of the Universidad Politécnica de Madrid, and I will present our paper, which is called A Framework and Evaluation Methodology for Autonomous Drone Racing. So I will put the video that we have made for this presentation.
The sound is very low.
The audio can you hear the audio?
No,
Okay, so
can hear. We can hear the audio.
I don't know why.
Maybe in the setting,
Mm,
in the audio setting.
When you share the video, you have to make sure that you press the option of using sound. So
Okay,
when you
okay.
click share screen at the bottom of the next,
Okay.
click on that.
In this video, we present a novel framework and evaluation methodology for autonomous drone racing. In recent years, autonomous drones have been increasing their application in different tasks like firefighting, search and rescue, or inspection in dangerous environments, such as tunnels or caves, or even erupting volcanoes. Their maneuverability and capability to access hazardous locations without endangering human lives make them ideal for these tasks. However, the short time flight of these aircraft greatly limits their use in long-duration tasks. To take advantage of this, it is interesting to develop agile drones that can explore or traverse an area in short time. Autonomous drone racing is a great environment to push agile drones to the limit. The high speed and agile maneuvers required for this purpose increase the difficulties of locating, controlling, and generating trajectories. In recent years, autonomous drone racing competitions like IRO's ADR competition or the more recent Alpha Pilot have helped to improve the state-of-the-art substantially. However, autonomous racing drones are still far from reaching human pilot performance, and a lot of research has to be done to accomplish that. To test different techniques to get the best results, it is useful to work in a modulated environment that allows you to develop and validate different algorithms independently. In this work, a complete architecture system and an evaluation method for autonomous drone racing research is proposed. The system architecture that is presented in this work has been developed using the Aerostack framework, an open-source multi-purpose software framework from the development of autonomous multi-robot unmanned aerial system, created by the Computer and Aerial Robotics Group. The framework architecture is organized in the following layers. On the right, we can see the sensor-actuated interface layer, which is in charge of receiving data from sensor on the aerial platform and sending commands to robot actuators. Data provided by the simulator are included in this layer too. Next to this layer, the communication layer can be found. Our architecture uses this common communication layer that contains shared dynamic information between processes. This channel facilitates process interoperability and helps to reuse components across different types of aerial platforms. The following layer corresponds with the robot behavior layer, in which the robot functional capabilities, including motion control, feature structure, state estimation, and navigation, are implemented. Finally, the control layer executes a mission plan specified in a formal description. A behavior coordinated component is used to translate planned tasks into consistent activation of robot behaviors. The following is a more detailed description of the robot processes developed. All the set of behaviors that are responsible for controlling the movement of the drone are included in the motion control layer. This category includes simple behaviors such as takeoff, hovering, or landing, as well as more complex behaviors such as generating a trajectory and making the drone follow it. In order to realize aggressive maneuvers on a quadrotor, it is necessary to employ a non-linearized controller. We have implemented a quadrotor control algorithm based on differential flatness, inspired by the work made by Mellinger et al., with several modifications, so the output of the controller corresponds with angular velocity reference and the desired collective thrust of all motors. The input of this controller consists in the position, speed, and acceleration references provided by the trajectory generator. Due to the need of generating trajectories for the controller, a polynomial trajectory generation has been used. The trajectories are generated on a set of waypoints and are optimal in accelerations, which guarantees smoothness in the actuator commands. In order to achieve the level of control required, it is necessary to provide the best state estimation possible to all components involved. Aerostack Frameworks already provides multiple components for this task, obtaining data for multiple sensors such as cameras, for relative positioning to a certain object, IMU, laser sensor, depth cameras, or LiDAR. However, for the real flights, we decided to use the state estimation provided by an Intel RealSense T265 tracking module due to the ease of use and the reduction of the computational load of the onboard computer. Moreover, support to motion capture systems like OptiTrack is also integrated. Perception is a key problem in the proposed scenario, since UAVs need to detect and locate each of the gates accurately to be able to complete the full track. Since the detection and post-estimation of the gates is a difficult problem itself, to evaluate the rate of the proposed framework components without the influence of possible errors in perception, we place Aruco fiducial markers in each gate to estimate the relative position of the UAV's main camera. Each marker also encodes a unique gate ID, enabling us to design arbitrarily complex tracks. When the gates are located in the real world, it is necessary to plan the path that the aircraft must follow to pass through them and avoid other obstacles. For this approach, we consider two scenarios. In the first one, lack of knowledge of gate position is considered. The aircraft does not have any information about where the gates are located, so it has to begin looking for them in order to generate the waypoints to pass through the gates. As long as the aircraft passes through the circuit, new gates will be in sight, so the quadrotor can add these gates to its route. In this scenario, the aircraft is always considered to see at least the following gate. On the other scenario, we consider gate position awareness. The aircraft knows an approximate position of each gate of the circuit, so it can generate complete trajectories through all the circuit that must be corrected with as long as the gates are in sight. So it has to update the initial gate positions to pass through the circuit. This is how the majority of the autonomous drone racing competitions work. In both approaches, each gate center is treated like a waypoint in the path, and this waypoint position is updated as the quadrotor flies through the circuit. Whenever the quadrotor passes through one gate, this gate center is removed from the path. The following are the different experiments that have been carried out to validate the performance of the proposed framework. First of all, simulation experiments were done trying to accomplish a 5-gate circuit using the state estimation provided by the simulator. Then, two types of experiments were performed in a real environment. The first consisted of passing through a single door at different speed. In the second one, the objective is to go through a small circuit of 4 gates. In both experiments, the state estimation provided by the Intel sensor is used. However, in the first experiment, the motion capture system will be used to measure the error made by this sensor. To measure the performance of the system architecture proposed and the switchability of the different algorithms selected, several metrics have been used. For measuring the accuracy of the state estimation algorithm, we compute the root mean square error between the estimate state and the ground truth. To evaluate the performance of the controller, we decide to measure the trajectory following error, calculate with the root mean square error between the trajectory sent by the trajectory generator and the real trajectory followed by the aircraft. In autonomous racing, other metrics like the maximum speed reached, the medium speed, or the elapsed time to go through all the circuit must be taken into consideration. All metrics obtained from the different experiments were obtained automatically using an evaluation script on the raw data recorded during the flights. We use Gazebo Simulator for the simulation experiments. Here, a video of the system working can be seen. In the bottom right, a first-person view of the aircraft is shown, while in the left part, the data acquired during the flight are plotted. In green, we can see the trajectory generated, and we can observe how it changes when the estimation of the gate position is updated. The aerial platform used for the real experiments was a custom quadrotor, based on the DJI F330 frame. This platform was equipped with a Pixel 4 Mini as the aircraft autopilot, an Intel RealSense T265 tracking module used for state estimation, and an USB fisheye camera for the gate detection. Additionally, the aerial platform was equipped with a single board computer NVIDIA Jetson Xavier NX for onboard computing. All computation required for the real experiment occurred in this single board computing. In order to obtain the ground truth position of the aircraft during some experiments, a motion capture system was used. For localizing the aircraft inside the motion capture system area, several IR markers have been attached to the platform. Here, we can see the real flight experiment trying to pass through 4 gates. In the video, a security pilot follows the drone, but it does not take the drone control at any moment. As we could see, on the simulated flight, the system was able to complete the whole circuit at different speeds, reaching speeds up to 3.2 meters per second, with the trajectory following average error around 50 centimeters, which validates the basic operation of the system. To sum up, in this work, a modular framework for autonomous drone racing has been proposed and validated through several experiments, not only on simulation, but also on real environments, being able to fly up to 4.16 meters per second, and to go through a small circuit successfully using onboard computation. The state-of-the-art algorithms proposed for each module, combined with the evaluation metric proposed, constitute a baseline for research on improving autonomous agile drone flying. To improve this framework, a wider range of possibilities to choose for each module must be given, like adding model predictive controllers, learning-based gate estimation methods, or a visual inertial odometry estimator fused with other sensors to improve the state estimation. Moreover, the domain gap between simulation and real life is substantial when non-photorealistic simulators are used. Using a simulator like Flightner or FlightGoogles will help to develop and test algorithms that rely on images taken through the flight. Thanks for watching.
Okay, thank you, Miguel, for this interesting presentation. It's impressive what you do. So maybe we have time for some questions. I don't know if the audience has any questions. In the meantime, I have a question, Miguel. From your point of view, what is the challenge to design algorithms for racing? For example, control algorithms or state estimation. What is the more important challenge from your point of view?
Well, one of the most the challenge most these kind of algorithms are the low the small time that you have for compute the algorithms, and when you put all the algorithms into an onboard computing, the low capabilities of computing that this computer has compared with a desktop computer, for example, makes you force you to use algorithms which are not as good as you can use if you had more computational power. But having to compute all your algorithms in a small time, because when you fly at high speeds, the reaction time is so slow that you must use as efficient algorithms as you can get. And the same is in control, can be the same problem has to be in control algorithms, but also when you have state estimation algorithms, when you use visual algorithms for localization the drone in an environment. When you go at high speeds, motion blur tends to occur unless you use some event cameras or things like that. And this is challenging too in order to develop autonomous drone racing drones.
Yes, I think it's not easy. It's not easy. In this moment, what kind of control algorithm have you implemented in your drone?
in this work, we use an adaptation of the differential flatness based controller that was designed by Vijay Kumar and Mellinger, but we did some small adaptations in order to don't have to measure exactly the dynamic parameters of the drone, and let the autopilot deal with these uncertainties in the model of the quadrotor, and making it more easy to use in other different platforms, or if other researchers want to use in their own drones, in order to facilitate the use of this controller in different platforms.
Okay, so it's very robust, Alison.
Yes.
Okay, so thank you, Miguel, for this presentation.
You're welcome.
Okay, so we will continue with the next paper. The next paper is the number 2. I don't know if the author is here. Yes, it's here. Shinji, are you here? Okay.
Yeah, here. Can you hear my voice?
Yes, we can hear you.
Okay. And
Can you share your screen, please?
yes, of course. Such topic is decentralized trajectory generation technique for multiple systems. First, I will give the research motivation. Then I will propose the detailed method. Finally, the experimental results will be given. Recently, multi-agent systems receive many attention due to many such as cooperative surveillance, cooperative strategy, cooperative pursuit invention problem. It requires to generate safe, dynamic visibility trajectories in short time given the environments. However, it is challenging to satisfy all the requirements. There are many researches about the multi-agent motion planning problem. One popular approach is centralized optimization method. It can generate optimal trajectories without deadlock, but it requires time to generate these trajectories, especially for large teams, and it may have high time consumption, may fail due to optimization failure. Another method is centralized optimization method. Decentralized planning is receiving much attention due to space scalability. However, such distributed method cannot guarantee the completeness and may get stuck in obstacle-dense environment. In this work, we will focus on decentralized multi-U-boat trajectory generation method. Our goal is to generate smooth, safe, faster trajectories for multiple rotors in cluttered environments, given the initial and terminal conditions. We propose a centralized mental heuristic gradient frame method based on PC. This method has less computational burden, uses limited trajectories approximated with neural network. It can also have reduce the time consumption of trajectories and avoid deadlock. In our work, the planning problem of each quadrotor K is formed as optimization problem. We design the cost function in terms of smoothness, target prediction, and obstacle avoidance. We use the state estimation and prediction method to avoid the dynamic obstacles and use a cost to avoid static and non-convex obstacles. The optimization constraints for corrotor K have three terms: model of the corrotor, dynamic limits, and boundary states. This is the overview of our algorithm, decentralized MPC-based cooperative strategy. First, we set up the boundary state of this problem. Then, we use pattern swarm optimization, a great phrase-over, to select the relative optimal states while minimizing the cost function. The reason why we choose this grid-free method is that the replanning time is more uniform and size time improve the success rate. For each replanning process, the states of all corrotors are predicted and are considered in the objective function. Relative closest distance between the predictive trajectory of a corrotor and moving obstacles are obtained through the communication. Besides, there is a guided map to avoid deadlock. Finally, after obtaining this relative optimal target state, a series of reference states xk can be generated, solving the two-state boundary value problem. The first few states will be given to low-level dynamic controller, thus recomputing the system state and the current state xk can be returned for the next replanning horizon. The first part is the construction of the boundary state constraints parameters using time optimal trajectory to get smoothness and faster trajectory, and use the controlling control method to get the obstacle-free trajectory. Given the arbitrary initial states and target goal states, time optimal trajectory can be obtained by choosing minimum, maximum, or zero of the jerk. It is proved that this trajectory is quite suited for the dynamic of the real vehicle. Next, we use these BSCPs, boundary state constraints primitives, to train a neural network. We input the relative states to 4-layer fully connected neural network, and the output is trajectory, including 41 states. The table and the figure show the error of the approximation is satisfying our needs. Thus, we can use this collision neural network to save the time consumption. For the convex obstacles, we use a guided map. The map includes cost to goal, cost value to the goal, and the safety value to the closest distance to the obstacles. And after we get in this map, we can use this to get optimal action at each cell. This figure showing the performance of this guided map. If we don't have the map, the purple one may get stuck in this environment. After using this map to predict the information of future state and navigating corrotor 5 to choose an optimal action at each state, it can reach its destination successfully. Next, we will show the results of untypical position swapping. Each corrotor must reach its destination while avoiding obstacles like several pillows. In scenario 2, each corrotor must reach its destination while guaranteeing the flight safety in the vertical axis. In scenario 3, the co-routers must reach its destination while avoiding deadlock in the non-convex obstacles environment, like this. Next, to validate performance of our method, we make a compare with other recent multi-co-router trajectory planning methods. We assigned a start point of co-router in a 10x10 environment, and the goal points at the opposition to their start positions and shown in the figure. We executed the simulation with 8 agents and measured the success rate by the size of the agent, which means the ratio of the minimum distance to the collision distance. As you can see, the sequential convex programming method may have high optimization failure. On the contrary, our method shows a perfect success rate. The proposed method also have better performance in terms of time per iteration, which means each reclining time. The decentralized method shows good scalability with high number of agents compared with the centralized method. So the computation time will increase by the number of agents in this ICP method. With the same direct limits, we also compare our method with the relative Western polynomial method. The trajectory is shorter without collision in our method, which means the total trajectory execute time is less. Because we use GLT to get time of trajectory for the co-router. So as you can see, given the same environment and the co-router dynamic limits, the total trajectory execute time is longer in RSFC method than ours. To summarize our contribution, our method is a collision deadlock trajectory method. It is also a synchronous, decentralized, and scalable scalability method. We can also maintain the relatively less total fail time with higher safety ratio. Thank you for listening.
Thank you, Jinji Wang, for your presentation. So if you want, you can start your camera, if it's possible. I don't know if the audience has any question for Jinji. No? If not, I have a question. It's very, very interesting, your work. And can you tell us about the experimental platform you are using for your test? What kind of rotors are you using?
Thank you. And the platform we use is Crazyfile. It is a small co-router, and you can just send use the Vicon environment to send them the trajectories, and he will this platform will this platform can also be in real time, and you send them trajectories, and the Vicon environment will tell the Crazyfile where their position is, and this co-routers will fly the trajectory you want.
Okay, so the control algorithms are implemented in the onboard quad rotors, or are implemented in the computer and central computer?
So in this work, we implement this. We mainly calculate the trajectories on computer.
Okay.
And send the trajectories to the co-router. So that's maybe the future work we need to implement. We may need to implement this algorithm on the larger co-router. Maybe the co-router have its own computer. So yeah, I think that's the point. We need to do a little bit of work.
Okay. So the optimization algorithms and the trajectory generation, it's carried out in the computer, and after they send to H4 rotor. Okay.
Yeah. But this algorithm is a decentralized algorithm. It is not centralized. So we can also, if we have a computer on each crazy file, we can also implement this algorithm in real time.
Okay, so I see. And if, for example, in your algorithm, it's necessary to communicate between the quad rotors?
I think if we want to implement this in real time or in the co-router must need to share the information of each other, and because they use the other co-routers states to predict other co-routers state trajectory, and in this way can avoid dynamic obstacles. Other co-routers in this team for each co-router is a dynamic obstacle. Yeah, so if a co-router want to avoid a dynamic obstacle, he must predict its trajectory in the future. So they must need to know the relative position of its dynamic obstacle. So they must share the information of each other.
Okay, I see. So thank you very much. It's very, very interesting to work, and I think it's very important, this algorithm, in order to implement in real time on board. Okay, maybe as you say, in the future you can do that. So thank you very much for your presentation.
Thank you.
And congratulations for your work. Okay, so now we have time, but maybe the author of paper number 16, it's here. Maybe we can test your screen, Juan.
Yes. Hi, I'm here.
Juan Manuel. Hello, Juan Manuel.
Hello. I can share my screen.
Yeah, you can.
Yeah. I guess, can you see my screen? It's okay, yeah.
It's okay. So just we're waiting a minute. Just
yeah. No, well, it's no problem.
Okay, so I think we can go ahead. Okay, so Juan, you have the floor.
Okay, I am ready. Hello, everyone. Well, my name is Juan Manuel Fortuna Cervantes. I am a student of the PhD program in Applied Science at the Universidad Autónoma de San Luis Potosí. I am going to present my research project, texture classification for object detection in aerial navigation, using transfer learning and web-based tutors. Well, this work is done in collaboration with Professor Marco Tulio, Marcela Mejia, and Jose Salomé, and on remote collaboration with Professor Jose Martinez Carranza from INAOE. Well, I will start with a quick introduction. The use of microaerial vehicles, MAVs, has increased in engineering and civil application to explore an environment without previous information. Maps have been used in different environments due to the air AC control and implementation of algorithms through the computer vision. In tasks of classification, detection, and location of the target, in particular in autonomous navigation, a fundamental part is that of detecting and locating target of our interest. For this reason, computer vision has become an essential analysis tool. In this work, we focus on object classification in aerial navigation tasks, where texture is involved in a physical property of the object. Okay, the approach to the problem, object detection and location is an important issue for making decisions. We know not all have been solved. In the robotics area, object detection is a problem for the robots that are performing tasks in real scenarios and in real time. Given that the lighted condition in determining orientation, object identity, shape, color, and texture. Furthermore, the information may differ in outdoor and indoor environments, which vary the target information. And then, will the task of detection becomes more robust? Its description capability is limited to the recognition of the texture as a physical property of the object. In recent years, math applications for object detection tasks have been studied and developed. Several approaches are using deep learning, given excellent performance in application. For example, in some tasks for autonomous navigation, we find methodology for obstacle detection and avoid using architecture called AlexNet that allows classifying the image captured by the camera on board the drone. The learning of this architecture is transferred from the ImageNet database to improve the classification performance. Moreover, to detect object autonomous landing in this work, detection system is presented to solve one of the missions, including the IMAV 2019 in the indoor competition. They involved the implementation of the ESD7 on board the map. This network is used for its fast performance on low budget microcomputer with no GPU. Besides, in object detection tasks, the author proposed a deep learning approach to estimate the object center in a robust way. Also, generating a line of sight as it provides to be a solution to avoid collision with other objects due to complications such as varying illumination condition, object geometry, and overlapping in the image plane. On the other hand, many projects employ deep learning and web analysis in visual processing. For example, on image classification, the author mentioned that although CNN is a universal extractor, in the practice, it's not clear whether CNN can learn to perform a spectral analysis. Well, in this work, the author proposed an architecture called texture CNN to have this approach within the CNN. The idea focused on the fact that the information extracted by convolution layer is of minor importance to the texture analysis. They use a statical energy metric in the Fourier extraction stage. The architecture showed as improving in performance and reduction in computational costs. In terms of the texture classification in image processing application, the author proposed an architecture called Wavelet CNN to generalize spectral information lost in conventional CNN. This information is beneficial for texture classification, as it usually contains detailed information about the object shape. Furthermore, the model allows us to have fewer parameters than in traditional CNNs, so it's possible to train with less memory. In general, through the state-of-the-art review, we have observed that the computational intelligence algorithm improved detection strategy in micro-aerial vehicle application. This work proposes an approach based on transfer learning and web tutors. The system allows to predict or classify the texture in image transmitted by the camera on board the drone, whose objects are in under a scenario, we used Gazebo as in virtual simulation environment. We are only interested in texture recognition, mainly to know one of the characteristics of the object. So we limit the image plane to a region of the interest. As a result, the system will have the image in the RGB as well as grayscale version. These two images are the input for our proposed classification system. Next, well, described texture dataset was selected to be used. It contained 47 classes of 120 images in the wheel. This meant that the images have been acquired at the uncontrolled condition. This dataset includes the 10 division available with 40 training images, 40 validation images, and 40 test images for each class. Our experiment will create a new dataset with the distribution of 70% for the training, 50% for validation, and the remainder, the 50% for the testing. One limitation of the dataset is the number of the image per class. So it is decided to use transfer learning method to improve the classification performance of our model. The synaptic weights are based on the ImageNet database, which will fit the first extraction stage of the base architecture BG16. Before training, the hard wobble transfer into dimensional is applied to the one level. See figure 13. The factor of the one represents the level of the image decomposition. This new spectral information is essential for classification. Therefore, for set in the wobble domain, are automatically generated to determine the characteristic attributes for the each texture. This information can be combined with the spatial information of the BG16 network. Also, it's essential to mention that this process is only applied to the image previously compared to grayscale, performing the decomposition for a single channel. Fine. The first instance, the BG16 network was trained from the scratch. Result is not able to generalize it in its knowledge. Therefore, it is possible to use a transfer learning methodology. In the table 1, show the achieved performance of the pre-trained network proposed with the web filter fusion. It showed that the accuracy performance on the 3 set to validate the model, training, validation, and test. In the case of the pre-trained network, a sliding overfitting is observed. The model will be adjusted to learn a specific case and will be unable to recognize a new texture. On one to improve the performance of the model is to integrate the web filters. In this case, we achieve the elimination of the fitting and we similitude between the 3 sets, training, validation, and test. Besides, the value of the test set is highlighted because they are images that the model has never seen. In the table 2, summarizes the achieved performance of our classification system, as well as comparison to AlexNet, training from the scratch, TCNN, and Webelet CNN. My model has a similar performance to the others. Okay, other metrics evaluate the performance of the DTD dataset classes. The metric shows a precision, recall, LF1 scores are given when applying the classification report method, where it is necessary to improve the true levels and the prediction level of the model. The table 2 shows that the classes that the performance above 70% classification about the precision metric. These classes are the best for 70 classes in dataset. Also, in table 4, show the 3 random classes that the performance above 50% classification in the same prediction metric. This classes selection analysis provide the basis for the design of the texture cubes of the Gazebo environment. On the other hand, we can observe the correlation between classes about the test set by performing the prediction. In the figure 14, shows that the true level and the prediction level at the top of each texture. Okay, we create a virtual environment with the gazebo simulator, controlling and sending information from the camera on board the drone using the ROS framework. In the work presented in the figure 15, we positioned in a row the 10 cubes with the select texture. Therefore, the position of the cubes allow the evaluation of the prediction model during the aerial exploration. The idea of the model is to generalize the knowledge towards texture object. In total, 1,000 image captures were performed in renavigation recognition for each class. In the figure 16, showed that the proposed texture set, bubbly, checkered, honey striped, and studded, obtain a high correlation with their original level, about 60% accuracy. Okay, in the next figure, some images of the recognition set are shown with its original level and its prediction level. However, we can observe that the 5 test images incorrectly predict the freely lined, polka dotted, and zigzagged set. These 5 images related to the wall recognition set, except for fibrous, polka dotted, and zigzagged, which achieved at least 3% accuracy. This result allowed to us a gain perspective of the generalization of the model towards texture object. Okay, I would like to show a demo with 3 objects. We can see the level and the window on the application. Here we can see the prediction inference of the model during aerial navigation. First, we take off the drone and position in the front of the texture. Second, we try to position object in the region of the interest in the image. Consequently, we will obtain the object level, and if it has probability above the 70%, it will be displayed in the drone image plane. For the checkered texture prediction is okay. For the honey texture is the same. The prediction is okay. Then the student, the 3 object, well, the student texture has a high correlation with the frequent classes. Okay. Well, frequent. Well, the student texture has a high correlation with frequent classes. I can level in the image plane. Well, okay, in the conclusion of this work, there are 3 main topics. Number 1, the location and object detection tasks using visual information and challenging, particularly when objects exhibit repetitive texture. However, this tag open opportunity for various applications using micro aerial vehicles equipped with onboard cameras to be used for object detection and recognition. For instance, for parcel pickup, place recognition, and landing zone detection. Number 2, seeking to improve detection and recognition state. In this work, we have investigated the use of the spectral analysis in combination with deep neural network. In particular, in this proposal, we merged the additional create spectral furrowed maps to CNN learning. Also, it's shown that the model we use a chip to eliminate overfitting and better accuracy in the classification of texture. Number 3, the prediction model showed that the creation of the whispered understanding of the texture attaches to the object. Furthermore, despite having a low classification rate, it is shown that the model correctly classifies most of the test classes. Sorry. Okay, as the future work, this will test with other texture future, also seeking to carry out tests in real world scenarios. Well, this is my presentation.
Okay, thank you very much, Juan, for this interesting presentation. I'm very impressed always when I see algorithms for visual recognition, etc.
Yeah.
So I'm not expert in this field. So I don't know if the audience has a question. No. We have a question from Hugo Rodriguez. It is just an related question. Do you know if Gazebo runs in Windows?
Yeah, I think that well, it's possible. Well, I use Ubuntu when system operating Ubuntu. Is well, the word is better than Windows.
Okay. I listen that now it's possible to run Gazebo in Windows, Hugo, but I don't know exactly how do you. Sorry for the noise. Juan, for example,
Yes.
what is the interest to estimate the object texture? Because, for example, in the navigation, you have an object. The objective is to avoid. So no matter the texture, so what is the interest behind the texture classification?
Yes, thank you for your question. Well, that's interesting. Well, in the first, we want to improve the classification performance. Well, the result has to again perspective to the generalization of the model towards the texture object. For the fusion of the transfer learning and analyzed level, well, I have more results for the using only one method.
Okay. So thank you. I don't know. There are another question. Can you tell us about the computer requirements to develop this kind of algorithms?
Yes,
it's very
well,
expensive or not?
Yes, well, in my case, well, I don't have a computer with GPU. I try to use the computer with the other center in my university. Well, I have a NVIDIA card. The model was training in time for about 3 hours. Well, it's necessary to the results about the training.
Okay, so maybe it's not possible to implement these algorithms on board.
Yes, it's possible. Well, I think well, I can see the application in the event. Well, it's possible. In my case, I don't have well, I don't have resource for the implementation. I try to use environment simulation for the improve and the validate my methodology.
Okay. Thank you very much, Juan, again for this presentation, and congratulations for your work.
Yeah, you're welcome.
Okay, so thank you very much. With that, we finish this session called Autonomous Navigation 2. Maybe Jose has a message for us.
Thank you, Fermi. And that was the last session of the conference, which means that we have reached the end of this event. It has been only 3 days, and I feel like we have been here for the whole week, because it has been full of information, so many different people, so many great ideas, and well, everything has to end eventually. I hope you can see the screen. You are seeing me, but we have all the organizers now online. And then what I will do is just go to the presentation for the closing ceremony. So let me get ready. Okay. Yeah, right in time. So it is always tricky to move everything over here, but okay. So I will share my screen. You tell me whether you can see it. So I think you must be seeing the screen now.
Yes.
Great. So even though it sounded like I was complaining because we have been here for a long time, from my perspective, the reality is that I have been enjoying all these 3 days. I had the opportunity to listen to all the talks. Of course, I was attending the keynote presentations, having questions and exchange of ideas with the keynote presenters. It was quite interesting and very exciting. So I'm really hoping that everybody who is watching this now or eventually later on, they will find it also very interesting. So this is the closure ceremony starting now at 7. After 3 days, 3 full days of presentations, keynote presentations, we had panel sessions, and we even had some videos from one sponsor. And I just want to remind you that this whole event was organized by 4 institutions, INAOE, UTLAP, Benemérita Universidad Autónoma de Puebla, Sinvestap, and had it happened physically here in Mexico, we would have hosted you in Puebla City, the capital of the Puebla state in Mexico. And as I said it in the award ceremony, what you are seeing now at the bottom of this slide is a picture that Oyuki took this morning, right this morning, because we were struggling to find, we were trying to find, a picture for the proceedings, and all the pictures on the internet, they had this thing with the copyright, so we didn't want to risk it. So she went to the top of her flat, well, her building, and took the picture. And this is a very nice picture because, as I said, this is what we see almost every morning here in my city on the way to my institute. And then once you are at the institute, you have this view. And I find it very humbling because this is an active volcano. They always call them the volcanoes. I'm not sure if the one to the right is also a volcano, but it is a very large mountain called Iztaccíhuatl. The one to the left is called Popocatépetl. And there's a very nice story about these volcanoes, but I hope you get curious and you go to Wikipedia and find out about these volcanoes. But they are big, they are quite impressive to see. You get used to them because you see them every day. But from time to time, when you look at them, it reminds you, I think it reminds us of our place on this earth. So it is very nice to see them and appreciate them. So I really hope that maybe in the future, you will be able to come to Mexico and visit this very nice city. So in this conference, we saw the presentation of 27 scientific papers. The proceedings are online now. If you go to the website and you click on the proceedings or go to the proceedings, you will get them. You will be addressed to the place where they are found. So please go to them. They are open access, which means that everybody can put his or her hands on the PDFs and enjoy the contributions. We selected a group of papers that are going to be published in 2 scientific journals, the International Journal of Micro-Air Vehicles and the Unmanned Systems. So we have already contacted the authors, and we will arrange what is going to be next for the publication of these papers. And then we also had 3 awards that we presented this midday in the award ceremony. And we announced the winners of the best conference paper, the best technical application paper, and the best student paper. And I think the three of them were fantastic pieces of work. We also had two runners-up or finalists to the best conference paper. So these 5 papers really stood out with their quality and contributions to this field of micro vehicles. But then again, the rest of papers that we saw in the conference were also quite nice and quite interesting in terms of ideas and applications. And finally, we got the sponsorship. The company Luxonics was very kind to award these prizes. Each paper will receive one sensor, the OAK light sensor, and I'm pretty sure you will find it very very appealing because it is a very tiny sensor. It's a smart camera that can be mounted on board a drone. Not a very small drone, but certainly micro vehicle. It could carry the sensor. So we'll see what you can do with that. Hopefully you will do some exciting work and submit it to the next IMAV 2022. I just want to take a minute to remember that we got also very good keynote speakers. I think the presentations were fantastic. We saw from what is being developed in terms of UAVs or unmanned aerial systems here in Mexico, actually, by the Mexican Navy. As the Admiral said, 10 years of experience were described in this keynote presentation, and it was very interesting. And of course, the presentation given by Professor Guido de Kroon about tiny drones, agile drones, a swarm of drones. That was also quite impressive. And many of these drones or his work focuses mostly on insect-inspired artificial intelligence for these tiny drones. So what he presented was quite impressive, I would say. And then we also had the presentation of Professor Tom Richardson, which came quite in place for our city, because he presented what he has been doing with volcanoes and operations with drones beyond the line of sight, something that is quite complicated, and how he was using them to take measurements of the plumes from the volcanoes. Here we have our volcano, so we really would like to have Tom to come to our city and do some testing on this volcano that is active. We also had the presentation of Brandon Gilles, who is the CEO of Luxonics, and he not only talked about this smart camera that they offer, but also how it can be used with drone applications, and he unraveled the potential behind this sensor that is capable of running neural networks on the chip that is small and can be carried by a drone. So we were discussing how this type of technology can bridge the gap in between drones that are designed in a clever way and drones that have to behave in a smart way, like an aerial robot that not only has to fly, but that has to perform intelligent behavior, has to take intelligent decisions. And today we have these two amazing keynotes from Nicolas Marchand, who was talking about event-based control. And then he showed us all these algorithms for navigation, where it was capable of avoiding obstacles. And it was quite interesting to see that approach from the point of view of control. And we closed the keynote presentations with the participation of Rogelio Lozano, who presented this novel rotor for helicopters, or small helicopters. We had a very interesting conversation on different ideas and what is going to be the future of micro air vehicles, or in general UAVs as well. And something that stayed in my mind was that he also talked about endurance. So with his talk, we saw two key aspects in the IMAV conference, which is this thing of endurance, that we want drones or UAVs to fly as long as possible. And the second aspect, which is very important, the design. So how do you design drones, micro air vehicles, in a way that they become affordable, easy to use, easy to repair, that's something that it becomes attractive for the companies to be interested at, so they can be deployed commercially. So that's my best effort to summarize what we saw in these keynotes, but you can always go to the links on Facebook and YouTube. They will be there, I don't know for how long. I wanted to say forever, but we don't know, but at least they will be there. So you can always rewatch the presentations. And then we had two very interesting discussion panels with former IMAV chairs from IMAV 2016 and 2018, Professor Ben Chen, Professor Simon Watkins. They took us to remember these competitions, in particular the competitions. They show very nice videos about that, and of course the conference and the keynotes. So the discussion was also very interesting about different challenges that are still valid today, like talking about noise, whether we want noise for drones or we don't want noise, how to detect noise. And then, yes, of course, what could be used in different applications, like if we use drones for search and rescue, then maybe that technology will be more accepted by society rather than having taxi drones, for instance. So it was very interesting. And the second panel was, it was a bit more crowded with the participation of Professor Guido de Kroon, Professor Jean-Marc Mosqueta, Professor Pascual Campoy, and Assistant Professor Gutierrez Hattenberger, general chairs, in the case of Guido, of IMAV 2014, and he mentioned others, of course, and Professor Jean-Marc from IMAV 2017, Professor Campoy for the IMAV 2019, and Gutierrez was deputy chair of the IMAV 2017. And in this panel, actually, it was more remembering the events where we had these 4 presentations where they show pictures as well. And it was interesting to see different times of the IMAV events. And perhaps what I enjoyed the most is the description all of them gave about the IMAV, what the IMAV means, what is the main idea behind this event that is not only a conference, it's also a set of competitions for outdoors, indoors, and the spirit behind it, which is to foster innovation, to promote research, but moreover, to bring people together for them to exchange ideas, to learn from each other, and to enjoy the competitions, not only to compete for the sake of a prize. So that was a very nice message. I really enjoyed it. So after having said that, it's now the turn for me to say thank you to a bunch of people. Without their help, this event couldn't have happened. It looks like we're here in a confident way, trying to do our best. And of course, we struggle sometimes. We had some problems with the online streaming, but in general, before the conference, there was a lot of work. We had 1 year of preparation. And I have to say, for those who didn't know, that the original IMAV in Mexico was planned to be for the IMAV 2020, because we were planning competitions. We were planning not only the conference, and actually, when I approached my colleagues to propose them that we organize this event, that we bid for it before the international committee to see whether they would be interested in having the IMAV in Mexico. They were very excited, and actually I thought of them because I also thought that their institutions had the facilities for these competitions. And then we put everything together. We put the proposal, and we won the bidding. So it was very nice to have the news that we would organize the IMAV in 2020. But unfortunately, because of the COVID pandemic, it was not possible, and we decided to wait. So that's why we didn't have an IMAV in 2020. And then this year was not much better at the beginning. So that's why we decided to go finally with a virtual conference. But I also have to say that this is the first time ever that this event happens in Latin America, at least organized by Latin American institutions. So then again, after all of that, I want to say thank you to Dr. Cesar Martinez Torres, who originally was assigned the task to be the indoors competition chair. This indoors competition would happen at Universidad de las Américas Puebla in their facilities. So please, Cesar, if you can come to the front and say a few words, please do.
Thank you, Jose. Well, I think I have nothing to add to your comments. It was a shame that we didn't have these competitions in local, or not in virtual, but in real. But well, we are still working, and even probably if for the next years we'll probably have once again IMAV, but now in real. That's all. Thank you.
Thank you, Cesar. And next to you, we also got the support of the media staff from UTLAP. So a big thank you to them as well. They have been supporting us with a Zoom virtual room, and also with streaming live on social networks of UTLAP. So to all of them, Victor, Guillermo, Abraham, Omar, Subiel Vélez from TV UTLA, thank you. It has been very hectic, but you have been very supportive and very patient. So thank you very much. And I also want to say thank you to Dr. Jose Fermi Guerrero Castellanos. You saw him before this closure ceremony. He was the session chair of the last session, and he has been chairing other sessions as well. So please, Fermi, if you want to come forward. And I have to say that originally he was the outdoors competition chair. He found an amazing place here in the city where we were thinking of how the teams would deploy the drones, and for all these challenges that we propose. But well, please, Fermi.
Okay, so firstly, thank you, Jose, for the invitation to participate in this committee. For me, it was a great pleasure because I think that it's very, very important, and it's very necessary, this kind of event for the students, for the professor also around our country, because the drone, the robotics in general, it's an area that it's very important to develop in our country, because there are many opportunities in research and opportunities in industrial application also. So I think that this conference allow to see many perspectives around this kind of things. So thank you very much for the invitation, and hopefully in the next years we can to carry out this conference in live. So,
thank you.
Thank you.
Thank you, Fermi. Thank you for your kind words. And of course, thank you to the people who supported you as well, the media staff, Dr. Cesar Augusto Arriaga Octavio, Octavio Torres Gonzalez, and Dr. Cesar Augusto Arriaga, and of course the head of the Faculty of Electronics, and Dr. Luz del Carmen Gomez Pavon from BUAP. So to all of them, our gratitude for their support. And also a huge thank you to Hugo Rodriguez Cortez, our program chair. He was he's the one with the magic behind our program. So he really did a great job organizing all of these different sessions that we saw, how to put papers in different topics and areas. And I think he did an splendid job. So please, Hugo, if you're around, if you're still around, because I think I took a bit of time.
Hi to all. I just want to thank all actors for sending their work to this conference. I enjoyed the presentations, and I hope that we meet each other at the next IMAV conference. Hopefully not a virtual one. So see you next year.
Thank you. Thank you, Hugo. Thank you very much. And just to mention some people, Israel Cruz Vega, session chair, who supported us, Dr. Israel Cruz Vega from INAOE, Dr. Caleb Rascon from UNAM. He actually proposed a challenge, a sound detection challenge. He specializes in sound sources for robotics. He's an expert on that, and we were very happy to have him on board proposing this challenge, and he was meant to be a judge for that particular one, to be part of the indoors competition. But well, he still joined us, and he chaired 2 sessions this morning. I think he also did a great job. So thank you to both of them. And before that, sorry, from UNAM, from the National University, Autonomous National University of Mexico. And I also want to say thank you, a big thank you to Antonio Juarez Gonzalez, Dr. Antonio Juarez Gonzalez, who is, because the website is still alive, he is our website chair. When I approached him and I asked him for his help to design, propose and design a website for this event since 2019, he didn't hesitate to tell me, of course, we can do it. And do not worry, we will do a very nice website. My opinion is that he really did a very nice job. The website really was functional, very colorful, and I really enjoy every time I had to go online and see things on the website. And with him, he had a team of people supporting him. So to all of them, Juan Pablo, Esteban, Emmanuel, Jose Juan, thank you. Dr. Antonio, he's based with Universidad Politécnica de Tlaxcala, and he has been supporting us all this time. He couldn't be with us for this ceremony because he works a lot, but thank you, Antonio, if you are listening to this, and if not, you can watch it again, but I will make sure that I will say thank you in person. Thank you for your work. All of you must have seen the website. So it was very nice what he did with the logo, all these colors and all this animation behind. And I have to tell you that one of the members of the International Committee requested a couple of days ago, before the conference started, whether it would be possible to have a small clock. It didn't matter that it had to be fancy or not, just a clock in real time showing the Mexican time, well, especially the Mexico City time, date and time, because since we got people from different places in the world, they really struggle, and I understand it. It is very difficult to see another time zone when it is not yours. So it's never clear what time is it. And we were under the risk of not having authors, turning up because they missed the times. It happened to us in a conference, actually, that we didn't see the time clearly and we missed the talk. So he also did this small clock in real time for you to see. And just to give you an idea, in these last 3 days, from the 17th until today, the 19th of November, we got 1,000, a bit more of 1,000 visits on the website from different places in the world. So I think that tells you that there is a community there that is interested in these events, and they were checking out our website. So just in 3 days, 1,000 visits, which is roughly 300, more than 300 visits per day in average. So that's something very nice to see for our website. And then if you look at 1 month, so from today, 1 month behind, or the last 30 days, we receive more than 3,500 visits on the website. Many of them in Mexico City, actually from the center of Mexico City, which is quite interesting. But you can see that there are red spots all across the globe. From Australia, Simon Watkins is he's based at Melbourne. So, but yeah, we got people from different places. And then if you go 1 year, an entire year, so from today, if you go back, we have got 14,000, a bit more of, more than 14,000 visits in 1 year. And this website was put online almost 1.5 years. So I'm pretty confident that we got more visits than that, but with this application, I couldn't recover more than 1 year. And actually you can see that it is from February the 2nd until today. So 14,177 visits. And you can see that from many places around the world. So I think that tells you again that there is a community, there are people interested in this event, in this field of micro-air vehicles, and that is something to be proud of. And I really hope that this event continues for many, many years to come. So finally, the main institution that organized this event, the institution that has been supporting me, and the institution where I work, where I have my laboratory, IMAV, Instituto Nacional de Astrofísica, Óptica y Electrónica. It's the National Institute for Astrophysics, Optics, and Electronics, which, by the way, this year turned 50 years. They celebrated 50 years of since its foundation. 1 week ago, we had actually the anniversary ceremony for these 50 years. And I have to say this, something that I am very proud of, what I think we have contributed is that if you see this logo for the celebration of the 50th anniversary, there is a drone. And before that, the research on drones was something that if there was some research, perhaps it was not that relevant, I would say, because INAOE has 4 main departments: astrophysics, optics, electronics, computer science. And I think astrophysics has been one of the main aspects in research. So it attracted a lot of attention, especially because last year, INAOE collaborated into the obtention of the black hole image, if you saw the news. But well, with the work that we have done, I'm very happy to say that eventually, bit by bit, drones became also very relevant as a research topic, such that the person who proposed this logo also included a drone, a tiny drone. Well, it could be a large drone, but this is a quadcopter, exactly what Rogelio Lozano was talking, a very nice quadcopter that people like. So we are very happy for that. And then, of course, I had the support of different people at different times. At the outset of this organization, we had this team of students who were very enthusiastically participating in the elaboration of, for instance, the rules for the competitions. We were brainstorming about the challenges, and they helped us to write down these rules, to design diagrams, figures, and also to go to open the social networks, to do the administration of these social networks, and so many different micro tasks that they took over, and they helped us a lot. So thank you to all of them, of course, Aldrich, Jose Arturo, Antonio, Aaron, Sergio, Manuel, Rene. Actually, when we started this in 2020, at the beginning of 2020, many of them, they were PhD students or master students, and after almost 2 years, some of them have graduated, actually. So, but well, I hope that if you see this, thank you for your support and for believing in this project, and make sure that that you contributed to this as well. And also, thank you to the media staff from INAOE, Guadalupe Rivera, the head of the media departments at INAOE, Montserrat Flores de la Peña, who has been with us all the time, and Gustavo Hernandez. Thank you very much for all your help with this transmission, with this live transmission on Facebook. To all of you who are always behind the scenes, but you are very important, and without you, this couldn't have been possible, so thank you. And finally, to Yuki Rojas Perez. She's doing a PhD now at INAOE, but she has been herself to some IMAV events. She went to IMAV in China in 2016, and then she went to Toulouse, and her last IMAV was in 2019 in Spain. So she got a bit of experience. And again, she was very enthusiastically telling me in the morning, oh, I can go on the top of my building and take a picture. And she did, as she promised. And this is the picture that is going to be in the proceedings. So please, Yuki, come forward and say something.
Hi. So IMAV is a big event, and
sorry, your camera, we are not seeing you.
Oh, so this it's on my camera.
Yeah, the camera is open.
Okay, we don't see her. Well,
oh.
Speak out loud, please.
Yeah. Hi. IMAV was a big event. It is special for me, and I just thank you everyone for being part for this event. I hope you enjoy it, and see you next IMAV.
Okay, thank you, Yuki. I never saw your image, but we have your picture, so people may have an idea of who you are. And by the way, I have to say that she also contributed on the designing of the logo. She designed this fixed wing-like symbol, which is dressed up as with feathers, like representing the royal eagle from our Mexican flag. And she also designed this symbol for the Mayan number, which is in this case 2021. The one of the last year, sorry, 2020, was interesting because it had the 0. So that was very quite appealing. You know, we wanted to show off that because the Mayan numerical system, it includes the 0. That is something quite outstanding, you know, considering that so many years ago, not many cultures, even though they had numerical representations, they didn't include the 0 as a symbol, and the Mayans did. So we wanted to show that, but well, we will keep that image as a memory, perhaps to upload it on the website. But yeah, she contributed to the design of this logo. So thank you, Yuki, for that. Okay, and finally, as Pascual would say, not very interesting, but I have to say it. My name, again, is Jose Martinez Carranza. I am the general chair of the IMAV 2021. I have been here quite a lot, talking a lot, but really all the help I have received is from these people that I have mentioned. This event has been possible because of them, because of all the effort that they put together. So thank you to all of them. And I'm very happy, I'm very pleased with what we have achieved. And for the first time for this event to be held in Latin America, I think, and here in Mexico. Of course, I wish it could have been a physical event with competitions, is what we meant to do. But yet, I think we have done something important here. We got very nice papers, very nice keynotes, very nice discussions. And I hope that contributes something to the field. So the last thing, which is important, as you can see here, this is a history of different IMAV events, previous IMAV events, since actually it was a European micro air vehicle event or micro air vehicle event in 2004. So we have seen all these countries organizing the IMAV from China, Australia, the last one was Spain, and now Mexico. So where is it going to be? Well, I was asked to deliver on behalf of the next organizers for the IMAV 2022. And for that, I have to stop this one and let me bring the other screen. So give me a minute, please. Who wants to bet which one is going to be? Okay, let me. Okay, so the next IMAV 2022 is going to be in Delft, the Netherlands, the Technical University of Delft, bid for the organization of the next year, and hopefully we will have a competition as well. So not only a conference, but also a couple of challenges for a competition. So they sent me this slide to tell you about TU Delft, the oldest and largest Dutch public technical university located in Delft, in the Netherlands. It is ranked by QS World University Rankings, a very good ranking, among the top 15 engineering and technology universities in the world. They have over 26,000 students, 6,000 employees. And this is a nice picture of Delft. Yeah, it looks a lot like Amsterdam. There are many bikes as well. And yeah, you can see the windmills as well. So it looks nice. Oh, there are some drones as well, some quadcopters. So Netherlands, the place of swarms, maybe. Okay, so for the organization, we will have the MAP lab behind the organization, the micro air vehicle laboratory in the Faculty of Aerospace Engineering. And if you saw the keynotes, I'm pretty sure that you can imagine that the chair behind this, or at least as part of the organization, is going to be Guido de Kroon. Although Christoph is there as well, so we'll see. And hopefully we will have a conference and a competition aiming for physical, maybe a hybrid event with a suitable, flexible competition. We don't know the dates yet, but it is likely that it's going to be at the end of August. So please book that month if possible, or maybe at the start of September in 2022. And after having said that, we get to the end of this. And then, yeah, okay, so that's the surprise. It's going to be in the Netherlands next year. Hopefully we can go there. If there is a competition, I hope we can put a team together with all the organizers. It would be exciting to have a nice Mexican team competing. Right, so anything else you would like to say? Fermi, Cesar, Hugo? Hugo.
No, just see you next year in Netherlands.
Great. Well, once more, thank you for all your help. It has been invaluable and important. So to our audience, I hope you enjoy the event. All the papers are online already. They are open access. You can get access to them. And maybe at the end of this year or at the beginning of next year, you will see the special issues, which will show a selection of the papers from the conference. And those journals are actually open access. There is no cost for the authors. But then the advantage is that since they are open access, the public will be able to access to the papers as well. Great, thank you. Thank you very much. See you maybe next year, hopefully in the Netherlands. Take care, bye.